So here we are on day 4 of our Leetcode 75 strong challenge with our problem number 605, Leetcode 605, can't place flowers. This question appeared in the interviews of Amazon, Microsoft, LinkedIn, and some other companies. In this question, they're asking you have a long flower bed in which some of the plots are planted, some are not. However, flowers cannot be planted in adjacent plots. Okay. Given an integer array, flower bed containing zeros and ones, where 0 means empty and 1 means not empty, and an integer n, return true if n new flowers can be planted in the flower bed without violating the no adjacent flower rule and false otherwise. So in this question here, we have a list or an array, you can say, called flower bed, and it has a bunch of these elements here. What are these? So we have these ones and zeros. So one means this has a flower in it. This, again, this one means this plot has a flower in it, and all the zero means they're empty plots. Okay, so that means you can go and plant the flowers. But the thing is, there's a rule. Okay, left and right of that flower where you're going to plot or plant should be empty. So 0 means empty. So in this list, only one position I can see where you can plant flowers is this guy here. Okay, because if you look at the left of this element, there's 0. That means that's an empty plot. On the right of this is 0, which is an empty plot again. So that means you can plant one flower in here in this list, right? But if you go here at this element, on the left of that element is 0. That means you can plant the flower, right? But if you look at the right of that, we have 1. That means it's already occupied. This violates our rule. That means we can only plant one flower. And we have this integer here, 1, n equals 1. That means we can plant one flower in there. That means the output is going to be true, right? Let's look at the second example here. We have now n equal to 2. That means we have 2 flowers now. So let's see again, can we plant our flower here? One flower. So left of this is 1, that means it's occupied. So right away we can just ignore this because we cannot plant a flower in this position here. Let's look at the next position. Can we plant a flower here? So if you look at the left of that element, yes, it's empty. On the right, yes, it's empty. So yeah, we can plant one flower here. So that's one count. So we can plant one flower. What about the second flower? Because we have 2 total flowers here, right? So can we plant our second flower here? So if you look at if you're here, if you look at the left of this element, yeah, right now it's saying 0, but actually in the previous iteration, if you remember, you planted a flower here, right? So this became 1. So this became 1. So right away you can ignore this because our empty on the left side of this element is not empty anymore, it's 1. So we can only plant one flower. So count is equal to 1. We can only plant one flower, but they asked us to plant 2 flowers, right? So it's not working out. That's why the output is false. For the output to become true, you will have to plant all the flowers that have been given to you. So for example, if you had 2, you should be able to plant all those 2 flowers here following that rule. Okay, hopefully you get the idea of what's going on here. I'll just do a very simple approach. I'll actually just traverse or iterate this whole array here, and then I'm going to check where the left of the plot of that element and the right of that plot of the element, whether they are free, whether they are occupied, things like that. Okay, so that's how I'm going to approach this, and I'm going to start this right away. So as always, I'm actually going to specify my count variable here. As I mentioned earlier in the explanation, I'm counting, right, how many flowers how many flowers I can actually plant or plot in that array. That will be measured by this one. That will be counted by this one. So we will initiate that with count equals 0. And now I can actually traverse this list. So for I, just going to use a very simple for loop. For I in range flower bed, right? Or what flower bed? Length of that flower bed. Now inside the for loop body, I'm only going to look at the positions where there are no flowers, where there is an empty plot. Okay, that means where the element is 0. So, and we can ignore everything else. So in here, I'm going to be like, if flower bed I equals 0, only then do this logic, okay? And so we are completely disregarding anything that is 1. That means it's full. We don't care about that stuff, right? So if flower bed I equals 0, then do this stuff here. So what I'm going to do here, I'm actually going to do two things. The first thing I'm going to check is the empty left slot and empty right slot. So just going to write them down. Empty left slot. So this will be, again, if you're at position I, what's the left position of that? It's going to be I minus 1, right? What's going to be the right position of that? It's going to be I plus 1. So let's say it's going to be flower bed, I minus 1 equals 0, because that's what you're looking for, right? We're trying to check if the left of our position is empty. But the thing is, if you're here in the beginning of this list or array, if you're here, right, there's nothing left to this anymore, right? There's nothing left to this anymore. So I'm gonna start this with this. If I equals 0, that means your position is the first position of your array. That means there's nothing to check. So that means it's just going to be true. And why? In these examples, you have 1, but what if there's an example when there's a 0, right? So that means if the right side of that is empty, you can put your first flower here, right? So right away, I did this check here. The first check was of I equals 0, or if it's not the first position, then we're going to just follow the simple logic here. Flower bed I minus 1 equals 0. That means the left of that position, right? And I'm going to do empty. Similar sort of logic for empty right slot. If you're in the end, if you're in the end of this array here, right? And how do you calculate the end? You're gonna be like, okay, I equals length of the flower bed. Okay, length of the flower bed and minus 1. So that's going to be your this position here. So what happens if you're at the last position here? That means there's nothing on the right of that position, right? There's nothing here. It's the end of the list. There's nothing here. And imagine this is 0. In this case, it's 1, right? It's a bad example. But let's say we had a list that looks like this, right? And if this was 0 here and you were here at this final last position here, so there's nothing on the right. So we are checking that with this thing, nothing on the right. And imagine this was also 0. So in that case, you can make this 1, right? So that's what I'm trying to do here. But if you're not in the end, then you're just going to follow the simple logic again of flower bed. On the right, you're going to do I plus 1. I plus 1 equals 0. So you're checking on the right, the right element of that current element, right? So hopefully that makes sense. And when both of them are empty, that is, if empty left slot, because this is going to give you a boolean, so empty left slot and empty right slot, that means they're both empty. Then what we're going to do, we're going to increment our count by 1. Count plus equals 1. This will actually increase your count by 1. And we're going to, the thing that we are here for, we actually going to plant a tree there. How are you going to plant the tree? You're just going to do flower bed I, make it to 1. It was 0, now make it to 1. So this is how you're going to do it. And I'm also going to do a check here. If count, whatever the count we were doing, if it becomes equal to this n here or exceeds that, that means we are doing it well. Then count equals greater than equals n. That means just return true and come out of this loop. Okay, this will save us a lot of time if there are more elements to traverse in the long list. So this will save us time. It will come out right away of that loop. It will the function will return that true. If not, let's come out of this loop here and we're gonna return same thing here, count greater than equals n, and this will be a boolean obviously, and they're essentially asking just for the boolean. So let's see if that is the right answer and accepted. Let's submit this. Okay, perfect. So that was the right answer. Submission was correct. Pretty good memory here. Beats 91.42%. Runtime 39.24%. You know what? I'm gonna submit this one more time and let's see if actually that changes anything here. Then I've seen, yes, you see that? It changes the number now. It's crazy. And now the memory became 33.54%. So that's interesting. Let's look at the space and time complexity of this solution here. So for the time complexity part, if you could see here, we are iterating this array or list. All the elements are traversed just once using this for loop here. And if you look inside this, nothing sort of crazy is happening in here. It's just some comparisons and some assignments here. And that's pretty much it. There's no recursive calls. There's no for loops inside. So just because of this one loop here, since all the elements in the worst case scenario are traversed or iterated once, uh, the the time complexity of this solution is going to be O of n. Okay, so time complexity will be O of n here. So O of n. Okay, that'll be the time complexity. And what about the space complexity here? So for the space complexity part of the solution is going to be O of 1. It's going to be of constant space. The reason for that is the function modifies this flowerbed list in place, but does not use any additional data structure. So as you can see here, we are using this variable here, cont equals 0, empty left slot, empty right slot, and I, which is this guy here, which are used, but we are not really storing or making a copy of this list or something like that. So because of that, the space complexity is going to be O of 1, since we are modifying the list in place. We're not creating copies or anything like that. So again, the space complexity is going to be O of 1.